So we've used an awful lot this lambda phi to the fourth theory. Lambda phi to the fourth, the closest analogy is it's like the harmonic oscillator. It's a very generic theory. It pops up all over the place, but there's no one unique application to it. QED is more like the hydrogen atom. You know, it's a very specific thing worked out in great detail. And so when you just like studying general quantum mechanics and then turning to detailed study of the hydrogen atom, we're going to here spend a series, probably 3 lectures, on just QED by itself, just what's the physics of QED. Okay, so the Lagrangian is minus a quarter f mu nu, that's the E and M field, and if there's a fermion in it, which we'll tend to do fermions here in class at least, it looks like that. And then if there's a scalar, it's d mu phi star, it's a charged scalar field, d mu phi. And then, you know, some v of phi star phi. It just has to be an invariant under u1, under the phase change. And d mu is always d mu plus I q a mu, that's the case. And so there, that defines QED. One of the initial features that's interesting is charge quantization. The charge appears in integer values. It's, okay, most often you see it n times the electric charge, but it's really n times the electric charge over 3, because in fact there's charge minus a third and charge 2/3 guys, but it's still quantized. It still ends up being quantized in these units. And this is not a consequence of QC, so it's of QED. Okay, so that's an oddity. So it's all, in a way, an indication there's something more going on, and it can be predicted in other theories like grand unified theories where it bring all the interactions together. But it's not here. Charges could be anything. The one thing that QED does, though, and this is actually pretty important, is if the bare charges are quantized, implies the renormalized charges are quantized. Okay, and that's a biggie. Okay, it's actually not trivial at all, because if you think about when we renormalized lambda, the lambda phi to the fourth, the renormalization there depended on the mass of the particle. If you go back and look at the formulas, there was a log m in that. Here, by some very important identities, the Ward identities, so this is due to what's so-called Ward identities, the charge renormalization turns out to be independent of whatever particle there is, which is good, because if it'd be extremely puzzling if the physical charges were quantized, yet this wasn't true. You know, so if you had to start with some strange ratios of charges and the bare charges to get the physical ones to be integer values. So I have a homework plan for you guys on the word identities to show you that, because it's an interesting feature of the theory, but extremely important in the long run. If that wasn't the case, nature wouldn't be neutral, the universe would blow apart, and all sorts of terrible things would happen. Okay. So that's one thing. The other thing that I want to do at the start is gauge invariance. Okay. Now, gauge invariance we've talked about before. It's a mu goes to a mu plus the derivative of some scalar quantity, a function of x. That's the gauge transformation, and the theory is invariant under it. But let's look at not just the general concept, but in matrix elements. There's a particular consequence of that in matrix elements. Okay, and here's how you get there. Remember, when we found the photon field, we wrote this as the integral d3q over 2 pi cubed, 1 over 2 omega q. And then there was creation operators, polarization vectors, e to the minus I q dot x, plus this Hermitian conjugate. Okay, so we end up taking matrix elements of states of momentum q. Well, think about this gauge change for the moment. If lambda of x is some integral d3, or actually let's make it d4q. It's actually an arbitrary function of space and time. Some lambda of q, e to the minus I q dot x. Then if I bring down let's put a d mu out in front, so d mu lambda, well, the derivative just brings down a factor of q mu. Okay? So I just take the derivative with respect to x there. Okay? So the gauge transformation here is like taking this decomposition and adding a term like that to it. So the gauge transformation is epsilon mu of q and lambda goes to some epsilon mu of q and lambda plus some number, an arbitrary number, times q mu. Okay, so in momentum space, that's what would happen with the gauge transformation. Oh, there's an I. Yes, there is an I. Thank you. Minus I. There's no I because I was focusing on something else, yes, rather than getting my math right. Okay, but lambda is completely arbitrary, so the fact that it's imaginary doesn't make any difference. Okay, so there's some transformation like that. So now let's imagine this a matrix element. Okay, so you've got some stuff coming in, you've got some interaction, stuff going out, and we're going to take a photon, momentum q, polarization vector epsilon mu. Okay, so it's of q and lambda. Okay, this matrix element, if I write minus I m, would be minus I epsilon mu of q and lambda, that's the external thing, times something else, which is mu. Okay? Everyone okay with that? But if this is to be gauge invariant, it has to be invariant under that transformation. And so if I take epsilon mu and replace it by q, so by doing this, the q piece can't give me anything. So this tells me that q mu mu equals 0. Okay, so gauge invariance, okay, it's better, tells us that whenever we find some matrix element, and these things can be pretty complicated, these matrix elements, because you could be having lots of stuff going on there. If you have any photon with some momentum q, you take away the polarization vector, you dot q into it, and you have to get 0. Okay. So let's do an example. Let's do scalar QED. This is the simplest example. We have this vertex there, P1, P2, Q is P, if I draw the arrow that way, is then P1 minus P2. And this matrix element is minus I E P1 plus P2 mu, and then I'd have my epsilon mu. Okay, if I was just writing that guy out. Then if I take q mu mu, that's q mu times, the minus IE is sitting there, but then P1 plus P2 mu. Q is P1 minus P2, so this turns into P1 squared minus P2 squared. Each of these is equal to m squared because those particles are on shell, and so I get 0, just as advertised. Okay. If I do the same thing with a fermion, then mu is replaced by minus IE u bar of P2, gamma mu u of P1. All right, everyone remember those guys? Those are the spinners. And then q mu m mu is minus IE u bar of P2. And what sits in here is P1 slash minus P2 slash u of P1. And now the Dirac equation takes this guy and says that that's equal to m, and this guy's equal to m, and so that's also equal to 0. Okay. So these are the simplest consequences of gauge invariance, but you always have to impose that. Now, one of the things you'll see later on, so this is the direct fermion coupling, but if you take some composite state, like the proton is a composite state, you'd write out a more complicated matrix element than this. It's not just the simple coupling from the Dirac equation. There could be anomalous magnetic moment terms, which maybe I'll have a chance to get to. But you'd have to impose this condition, so the general form has to satisfy the gauge invariance condition. Okay. Questions? We're going to use that today, so let's hold that in our head. We're going to start off then, how do you analyze this theory? Okay, so the first thing you do when you do this is you read the Lagrangian. And we've been doing this as we go along. So this is your pathway for any two. You know, you read the Lagrangian and you write out the Feynman rules. That's minus IE gamma mu for a fermion, or minus IE P1 plus P2 for a boson, and then there's a one like this for a boson. So we've had practice at reading the Lagrangians, and then you look at tree level things, tree level processes, and we've done that too. We do scattering amplitudes, and we've done diagrams that look like that. So the tree level stuff is, we've been doing. That's pretty easy stuff. The third thing is we're tougher. We have to renormalize at one loop then. Okay. And then predictions at one loop. Okay, and if that's not good enough, you move on and you do two loop. But we won't do that, of course. That's for the experts. So the renormalization comes in a set of things. There's going to be mass and wave function renormalization. For the fermions, there's wave function for the photon. There's going to be charge renormalization. Okay, so we have two parameters, mass and charge. In the Lagrange, we have to renormalize both of them, and then wave functions for both the types of particles. Okay, so that's our path. Let's do electron mass and charge. And wave function. Okay. I'll do it with fermions. The fermion business is a bit new. Okay, so our diagram is this guy. So we have an electron with momentum p, splits into a photon of momentum k, p minus k, and comes back to an electron of momentum p. Okay. This is minus I sigma of p is the definition of the name of it. Okay. So as before, we would sum, we take the free propagator, we take propagator with the sigma there, we take the propagator with two of them, etc. And this sums takes what was originally I over p slash minus m0 plus I epsilon and takes it into I over p slash minus m0 minus sigma of p plus I epsilon. Okay, at higher orders, you have to include other diagrams. sigma. So you start with that guy, and then there's diagrams that look like that. Plus, there's higher order diagrams, but we're just doing one loop. Okay, Feynman rules. Okay, so minus I sigma. P. Okay, so it's integral d4k over 2 pi to the 4th. Now let's just write this out. Now, remember, we draw the diagrams going this way, going from left to right. We write them going from this being the early side, that being the late side, so we write them from right to left instead. So the first vertex, that guy right there, I'll call it minus I e gamma mu. I'll stick it over there. This is a matrix, so the order does count. Yeah. Then we hit the propagator. It's I over p slash minus k slash minus m plus I epsilon, and then we hit the other vertex at the other side right there, minus I e gamma mu. And then there's the photon propagator. It doesn't make any difference where that you write that. Let's write it out here. That's just a number, not a matrix. 1 over k slash plus I epsilon. Okay. So what's in between the brackets there then is a matrix. Okay. Now I'm going to have you play with this, and I'm trying to decide whether it's worth having you do it. I'm not going to do it here. I'll do something else a little bit more. But you can see it's a matrix. I'm going to give you soon some identities that help get rid of these extra gamma matrices here. But as a matrix, it's going to have a term that looks like a constant and a term that looks like gamma matrices. So we're going to do the following. We're going to expand this. Now, we know that it depends only on P. That's the only variable. So sigma of P is going to be written as delta M, and then I'll just write it as the following way: Z2 minus 1 minus 1 P slash minus M. Okay. Plus higher orders. Okay. So let's accept that from this. Z2 is going to be one of the wave function renormalization constants. In QED, you've got 3 constants that are going to get called Z1, Z2, and Z3. Z2 is always associated here with the fermion renormalization. Z3 is going to be photon wave function renormalization, and Z1 is the vertex correction. Probably not done today. Okay. If you take that naming, then I over P slash minus M0 minus sigma turns into I Z2 P slash minus M physical. I'll call it M renormalized. Okay, so if we do our same tricks, then all you do is you read out of this is you find delta M and you find Z2 from doing that calculation. So we end up with the following. I'm not going to do this for you, but let me just show you what it looks like. Delta M looks like 3 alpha over 4 pi M0 log lambda squared over M0 squared. If I use Pauli Villar's regularization, and this thing turns into 2 over 4 minus d in dimensional regularization. Okay. One of the features that's important for this, that's very relevant for a lot of physics, is that it's proportional to m. That's the proportionality sign, to m0, to the mass itself. So if the mass were 0, the mass shift is also 0. So if m0 equals 0, delta m equals 0. And so no mass is generated. This is actually important because it tells you that the massless limit is protected. I'm not prepared to do it here, though I guess I could do it if people ask. But there's a symmetry that's called chiral symmetry, which is an extra symmetry that happens when m is equal to 0 and protects the mass. So that's a symmetry when m is equal to 0, and it protects it. And so this is going to be made a little fancier, but that's the factor there. Okay. Z2 is the renormalization constant, wave function renormalization. And the way you get it is this Z2 minus 1 is minus d sigma dp slash. You just calculate away and take d sigma dp slash. Okay? That's going to be relevant for your ward identity homework. So, nothing much of deep content in this one, aside from what eventually is going to be the ward identity. Might as well just say it for you. After I've defined Z1 and Z2 are going to be the same, and that's where you're going to have your homework on, showing that. Okay. The one that does have a lot of content is the photon wave function. Okay. There's an awful lot of content in this. So we're going to play with it a little bit more, just so you're a little bit more familiar with it, and use it to show you a couple interesting things. So what happens for photon wave function renormalization? Okay, at one loop, what can happen is you take a photon coming along, so it's coming along with momentum q. It splits up into a fermion and antifermion and comes back together to become again a momentum q. So let's take one of these fermions and call it k plus q, and the other one then is k. That conserves momentum. This guy here. So I start with a mu over here, photon momentum mu, comes out here with photon, polarization mu, polarization nu. This is defined to be I pi mu nu, that's a function of Q. Okay, this is the vacuum polarization. Okay. So, in principle, you sum over all relativistically charged, all charged particles. Okay. So, there's a whole bunch of terms here. We'll see in the end that the finite pieces of this, so the finite pieces of this are small at low energies for heavy particles. So, there might be some particles discovered at the LHC that go into that sum that we haven't learned about yet. We're not sensitive to that at low energies, despite the fact that the diagram includes them in principle. Okay, so let's write out this. So for fermions, I pi mu nu of Q is, well, there's an integral d for k over 2 pi to the fourth. There's a minus sign that comes from the Feynman rule about extra minus sign for closed fermion loops. And then we start the Feynman rules. All right, so here there's this issue that it doesn't, we could start anywhere on this diagram. So let me start there, and I'll walk around the fermion lines, putting stuff next to each other in the right order. So I'll follow that around. Okay, I start minus I E gamma mu. The next thing I have is I over k slash plus q slash minus m. That's the propagator on the top. I come to the next vertex, minus I e gamma nu, and then I have the propagator on the bottom, I over k slash minus m. Okay, I get back to the same point, and the matrix, this is a matrix. It multiplied this on the one side, this on this. This matrix then, the index that sits over here comes back as the same as the index that starts on that side. So this turns into a trace. Okay, the trace is overall the fermion indices. Okay, I think I worked that out once. I did this in a little more gory detail once before, but I'm happy to take questions about that part. Okay, the nice property of the trace is that it's cyclically invariant, so I could have started at any place on this, worked my way around, and got the same formula, because the trace, I could stick this over on that side, etc. The trace is cyclically invariant. Okay. Now this is one of these guys for whom we can do one of these gauge invariance tests. So gauge invariance would say Q mu pi mu nu should be equal to 0. Okay? Or Q nu. Q nu is the same. Okay? So that fixes the structure a good deal. Let's check it. it's not at all obvious at this stage. If I take Q mu dotted into here, basically that takes, I multiply Q mu by gamma mu here, so it's Q slash, and I've got a whole bunch of stuff that doesn't look like it's zero. It doesn't look like it's about to vanish. So let's do it. So Q mu I pi mu nu as well. There was the minus. Let me just pull out a bunch of stuff here. Let me get rid of all the I. So there's two factors of I, and the propagator is minus I is there. They cancel, so it just pulls out a factor of E squared. Minus E squared integral d4 k over 2 pi to the fourth trace. So for what I'm about to do, let me use the cyclic property. I need to write Q slash here because that's what I've got. But I'm going to take this propagator and stick it on the other side of it, just to allow us to mentally do the rest of the calculation. So I'll have 1 over k slash minus m, Q slash 1 over k slash plus Q slash minus m, and then I still have a gamma nu left over. Okay, we can sort of, you see both of them there? I've taken this guy, used the cyclic property, put it over here. Q mu gets Q slash, and then propagator gamma nu. Okay. So the way we do this is, when you show this, is you take that Q slash and you write that as k slash plus Q slash minus m minus k slash minus m. Okay, so I add and subtract k slash minus m. And by doing that, you see that this thing, this Q slash, looks like either one propagator or the other, and they come with a minus sign. Okay, so if we write that out, I get trace. Well, the first term there cancels that first propagator, so you're left with 1 over k slash minus m gamma nu. And the second one kills the k slash minus m propagator, so you're left with 1 over k slash plus q slash minus m gamma nu. Okay. So at this stage it still doesn't quite look zero, but it's getting close. You then define, in the second term, you take k plus q, call it L, and use d4k is equal to d4L. Then the second term looks just like the first term, and then this goes to 0. Okay, so we get q mu pi mu nu is equal to 0, as expected. Okay. But so that's true. That's the right answer. But let's just think about it for a little bit here. One of the troubles with this is that both of these terms are divergent. Okay? And so some of the manipulations that you do with divergences sometimes lead you astray. And so, is that true or not? And if you tried cutting this off with a cutoff, the shift wouldn't be correct. Okay, so if you use the cutoff, integral d for k up to some cutoff is not the same as the integral d for k plus q up to some cutoff. Okay, by shifting it, if you try doing it, this q, let's imagine it was a big number, can shift you past the cutoff even, if you take some finite integral. Likewise with Pauli-Villars. Okay, if I did, so it's Pauli-Villars, remember, is taking the usual propagator and subtracting off 1 over k slash minus lambda. So let's look at this. Q slash minus m minus 1 over k slash minus q slash plus q slash minus lambda. Okay, now so Pauli-Villars cuts off these propagators by taking the mass and replacing it by a very large number, and then at the end you try taking the cutoff to infinity, and so it should drop out. Okay, so just mentally do this here. If you take the first terms, the same identity works. You take in last terms, the same identity works. You get the difference of two things, and if you just shift them, it works. However, if you take the cross terms, it doesn't work. So take k slash minus m, q slash, and 1 over k q slash minus lambda. You try adding and subtracting, you don't cancel that propagator. Okay, I have worked it all out. I don't know if it's probably not worth showing you in gory detail. But these terms then do not cancel. Okay, so if you just do the exact same calculation, you get q mu pi mu nu not equal to 0 in that. And if you just do so you end up in neither of these. If you do this, you end up with pi mu nu at q squared equals to 0. Well, it's some number times this cutoff squared, whichever way you put it in there, times g mu nu. Okay. I'm not going to follow it through, but if you do this, well, I'll point out where it would occur. This gives a photon mass proportional to lambda squared. Okay. So yeah, there's an alpha and 3 pi, something like that, in front of it. So these guys are bad. That's you draw your typical sad face on that guy. That's not to be liked. So what we've learned from this is that cutoffs and Pauli-Villars naively applied violate gauge invariance. Okay, so that's a bit funny. Something that you do at the very highest energies has screwed up your physics at low energies. So the old style way of doing this, if you go back to old books, you just remove it by hand. You calculate it, you throw it away, and that's it. The new style, you just don't do this. You use dimensional regularization. Okay. So it's things like that that make dimensional regularization so valuable. Any questions about it? That's an important cultural lesson that's needed. Okay, with that out of the way, let's assume that we don't do anything that violates the gauge invariance, and then the structure of the vacuum polarization has to be pi mu nu of Q. Well, has to have the form Q squared G mu nu minus Q mu Q nu times some scalar function. That's a function then of Q squared. Okay. The only variable we have around is Q, and then that particular combination satisfies Q mu pi mu nu equals 0. That works. So you take it, the first term, dot Q mu into it, this becomes Q nu. Just G mu nu just changes mu to nu. And then the second term, you dot Q, and this becomes Q squared and Q nu. So those two terms cancel. Okay. So that's good. This then complicates our propagators a bit. The propagators, then, if I write out okay, so I take this guy, mu and nu. Remember we wrote that before as minus I G mu nu over Q squared plus I epsilon. Now we're instructed to do this plus that plus that plus dot dot dot, and sum all those. So now, okay. So in some process, you then, when you have a propagator, you then do the following. You'd then do, so for example, let's put it over here. You take that diagram, and then you take this diagram, and you take that diagram, etc., and you sum them all. Okay, and what I'm about to do, I want you to think about these guys being on the outside, because I'm going to have to do some. I have to drop a couple terms to get the form I want. Okay, so let's just do it. So this would start off as minus I G mu nu Q squared plus I epsilon, and then the second term would be plus minus I. Well, I've got a propagator sitting there, so let's call that sigma lambda minus I G mu sigma over Q squared plus I epsilon. Then I end up with, I'll write that in a minute, okay? Then over here it's minus I G lambda nu over Q squared. And sitting in here is Q I'm a little worried about my signs. Let me copy from my notes just because it's sigma lambda, q lambda, q sigma, pi of q squared. I've got a minus sign difference here, but I also am probably missing an I somewhere. It looks like 1, 2, because it was I sitting up there. Yeah, this originally was defined as I pi mu. All right, let's put the I there and okay, just plug away. Okay, so here, then there'll be higher order terms. But here now we have two types of terms. The first term is the one I want. So the first term, the Lorentz indices go mu sigma, sigma lambda, lambda nu, which just turns into g mu nu. Okay, if you just, mu is equal to sigma, sigma is equal to lambda, lambda is equal to nu. So that just turns into g mu nu. And these guys has q squared times q squared divided by q squared. There's a 1 over q squared for that piece there. So the first piece then turns into minus I g mu nu over q squared 1 plus pi of q squared. And the higher order terms keep that going, plus pi of q squared plus dot dot dot. It just keeps being higher order powers of pi, if done right. Okay. The next terms there turn into, okay, so mu is equal to sigma. Sigma then becomes q mu. Lambda is equal to nu. So this q lambda becomes q nu. So there's a q mu q nu pi of q squared over q to the fourth. Okay, so this guy, if we'd been a little bit more subtle in what we were doing before, this guy looks like it changes the propagator, and to some extent it does. But if you use it in any diagram, these guys disappear from q mu times that upper vertex, So this, if I'm putting this in the propagator here, here's a q dotted into that upper vertex there, and q dotted into the lower vertex. When I sum this, I already demonstrated that q dotted into those vertex functions gives 0 by using either Klein-Gordon or Dirac equations. And so those guys always disappear. Okay, everyone buy that? Good. If you buy that, I'm happy. You sum it then, and you get minus I g mu nu over q squared 1 minus pi of q squared. Okay. So here's where if I had a piece that didn't go like q squared but went like lambda squared, I would have a photon mass in addition. So I wouldn't have had this cancellation. This would have summed up to a photon mass. But here we don't have it. So there's no photon mass. If we again try defining near the pole, if we write pi of q squared is pi of 0 plus q squared pi prime of q squared plus dot dot dot, and then the propagator looks like, near the pole. If I just keep this leading piece, I get minus I g mu nu q squared 1 minus pi of 0. Okay, that's defined as minus I g mu nu. Z3 is what it's called, over q squared. Z3 then is 1 minus pi of 0. 1 over 1 minus pi of 0. That's the wave function renormalization constant. So the way you have to get rid of that is just like we did before. You define A mu 0 is Z3 to the 1/2 A mu renormalized. That's the physical one, and it just shifts it into various places in the Feynman diagram. Okay. Good. So that's where the vacuum polarization first comes in. This term right here, this q squared piece, is also going to be important. We'll come back to that later. That's part of the Lamb shift. And if I take this to high momentum, that's going to turn into the parts of the running coupling constant. So we're going to do 2 more pieces of physics out of this even after today. One will be Lamb shift, the other will be running coupling constant. So there's physics there. That's why this one is important. I want to spend a little time calculating this for you, not in complete detail, but because it's so important, it's just worth seeing a couple features. Okay. First, there's a bunch of identities that I haven't had a chance to say much about, so let's talk about them here. We have to calculate the trace of gamma mu 1 over k slash plus q slash minus m, gamma nu 1 over k slash minus m. That's our operator. Okay. So the typical thing one does here is you write 1 over k slash minus m by multiplying and dividing by k slash plus m. Okay, so this turns into k slash plus m over k slash squared minus m squared. But anything, anything you have k slash is just k squared. Okay, that's an identity. If you have any a slash is just a squared. If you want, it comes from, you can write this as g mu nu times. Okay, so this is k slash plus m, k squared minus m squared. And now this is a real matrix. Okay, this is 1 over a matrix is an odd quantity. It really means this matrix upstairs, number downstairs. Okay, so what we have to do here is there's all this, the propagators k squared minus m squared, 1 over k plus q squared minus m squared, trace of gamma mu k slash plus q slash plus m gamma nu k slash plus m. Okay. So quickly, let's just quickly give you some identities. Okay. So if I have trace of the unit matrix, okay, that's equal to 4. Okay, these are 4 by 4 matrices, so you trace that, you get 4. If I do trace of one gamma matrix, that's 0. All these gamma matrices are traceless. If I do trace of 2 of them, so let's take some A slash B slash. Okay. Now you can, this is cyclic, the trace is cyclic, so it's trace, now I could write it as A slash B slash plus B slash A slash with a half there. But if you think of what those are gamma matrices, so that's the anti-commutator of 2 gamma matrices. So this is 1/2 times trace of, well, becomes 2 G mu nu A mu B nu. So there's no matrix anymore. That's the trace of the unit matrix. So this is then 4A dot B. Okay. Trace of any odd number of gamma matrices is equal to 0. And that's not that hard. You'd use, again, cyclic properties. And the last one I'll give you is B slash A slash B slash C slash D slash. So 4 gamma matrices is 4, well, it's A dot B, C dot D plus A dot D minus B dot C. No, that's not it. A dot D times B dot C. A, D, B, C, yes. And then minus A dot C, B dot D. Okay, so the ones that come with plus signs are the ones that sit right next to each other. So AB and CD, or AD and BC sit next to each other. The one with the minus sign is the one that crosses over. So A and C, B and D. Okay, and it just comes, again, from permuting that. All right, so that's really all we needed for that. Okay, so then at this stage, then pi mu nu turns into q mu q nu minus g mu nu q squared. No, I haven't got there yet. Sorry. Blah, 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 blah. That's my next line. It's then minus e squared integral d4k over 2 pi to the 4th. These two propagators, k squared minus m squared, 1 over k plus q squared minus m squared. And then turns into 4 k mu k plus q nu minus plus k nu k plus q nu minus g mu nu m squared minus k dot plus q. Okay, And you can sort of see that if I can get both of these identities on the thing at the same place, there's m squared times the trace of gamma mu gamma nu. That gives me my g mu nu piece here, m squared g mu nu. And then there's the k, there's a 4 index 1 gamma g mu, k plus q gamma k. That gives me, using this identity, these terms and that last term there. And there's a bracket missing right here. G mu nu multiplies both of those. Okay. Okay. At this stage, you've got a bunch of integrals to do. You're going to do a dimensioning, and here's my present to you. It's our new Appendix C. Unfortunately, I noticed right before I handed, after I ran off all this paper, that there's a typo, or a series of typos, that something happened with the latexing program. And so this contains a lot of good stuff, but for the point of what we're doing now, if you turn to page what's called 511 on this thing, this is from our book, of course, but this is from the new version of the book, which is not yet published. There's mathematics in D dimensions, so we're going to do dimensional regularization. And besides these identities, which I gave you in 4D, there's the identities in D dimensions, and then there's also lots and lots of useful integrals. Okay, so several pages of useful integrals in D dimensions, so that you don't actually have to do these all the time. We've done them once for all. And I'll point out the typo for you. If you, let's say, go to equation 5.4a. Okay, so, and it happens in all these equations there. There's things that say like p minus q 2 m1 2. Those should be all superscripts. And it just continues in all these things. Somehow the superscripts didn't work in those definitions. So it's p minus q squared minus m1 squared, p squared minus m2 squared, things like that. Okay? So if you forgive that, then you've got a lot of useful stuff, and someday soon I'll have all those things fixed. Okay? So you then look at this, and now you don't have to do much. You just look at these, and this looks like various terms in those formulas there. There's M1 is M2, so that's easy, and you just read this thing off, and there's a bunch of algebra, but not too much else. And this then turns into Q mu Q nu minus Q squared G mu nu. So use Appendix C. There's an E squared over 2 pi gamma of epsilon over 2, 4 pi minus epsilon over 2, integral 0 to 1 dx, x 1 minus x, over m squared minus q squared x 1 minus x to the epsilon over 2. All right. So the only thing to point out is that there's divergences here. Divergences there. And there is still some residual q squared dependence that sits here. It looks like it's going to be trivial, because if you let epsilon go to 0, this thing would just be 1. But it's not, because remember, we have to expand. So the divergence goes like 1 over epsilon, and you take a to the epsilon, whatever a is, anything to the epsilon, write that as e to the epsilon log a is 1 plus epsilon log a. So there's a bunch of factors like this 4 pi there's a log 4 pi. Oh, I forgot my mu to the epsilon. There's a mu to the epsilon there. And then this guy also becomes a log. Okay. So this turns into, here's the full expression, pi of q squared then, the scalar function is e squared over 6 pi squared, just to show you what these things look like. 1 over epsilon. Epsilon is 4 minus d, plus log 1/2 log 4 pi, minus gamma over 2, minus 3, the integral dx, 1 minus x, log of m squared minus q squared x, 1 minus x over mu squared. Okay, well, and I guess the best I can do here is just to write out a couple of these terms here. So it starts off the same way. Okay, and you can sort of see if q squared goes to 0, there's just this integral x 1 minus x times log of m squared over mu squared. So it turns into, so this starts the same, it's minus 1/2 log m squared over mu squared, and the first term in the Taylor expansion is q squared over 10 m squared. Okay, so that expression that I have gotten for you right there is when q squared is much, much less than m squared. So I'm Taylor expanding around q squared is equal to 0. And the other one I'll give you because I want to use it later is the same sort of stuff. So there's the 0. It then turns into plus 5, 6 minus 1/2 log of minus q squared over mu squared. Okay, and that's it. When q squared is much, much bigger than m squared. Okay, if you give me a second just to point out a few nice features, you can sort of see this here. When q squared is much bigger than m squared, I just keep this piece, it's minus q squared over mu squared. I've got this integral, I've got some integrals to do here, including the x1 minus x in the log of that. But those are easy to do. So this guy here is here's pi of 0 and pi prime, the first derivative. This goes like 1 over m squared, so that's part of the reason why if m is a very big constant, very big mass, this term becomes small compared to the, let's say, the electron's contribution. The other thing to point out is that we've got this log of q squared here at high energies. It's scaled by mu squared. Mu squared is unphysical. This had better drop out somehow. And it will. But we will end up having to deal with that later on. Okay, so I have to stop there against my will, but there we go. Okay, so we'll come back and do a little bit of vertex renormalization and then show you how this pieces right here also give charge renormalization and how this turns into the running charge at high energies. Okay, so that's where we're headed. Okay, I'll show it to you just